In this lab, we observed movement at a constant velocity. The goal was to create a representation of Newton's second law, which is final velocity is equal to initial velocity plus force divided by mass times the change in time. Since our velocity is constant, we expect the acceleration of our object to be zero. This is because acceleration is equal to the change in velocity over a period of time, which would be zero since our velocity is constant. The object should maintain the same distance traveled per interval of time. To portray constant velocity, I took a video of a basketball rolling along the floor, with no forces acting on it. However, one of the assumptions we have to make is that no forces are acting on it, when in reality, friction is a force working against the movement in the opposite direction. However, its effect should be minimal, and we can expect to have an almost constant velocity, although our final velocity may be slower, or maybe a bit slightly lower than what would be expected. Here we have the video of the basketball rolling along the floor. I have put it into the program tracker, which tracks the distance it travels along the x-axis over a period of time, and then graphs it into a graph. As you can see, the graphic representation of distance over time, the slope is constant, and the graph is a straight line, which is what we previously predicted. However, we can compare this graph to that of a graph with perfect constant velocity, which we found by taking the first 2 points in our video and expanding that velocity over the total time. We can see that the distance traveled is slightly lower than the ideal situation of constant velocity, represented by the upper line with a greater distance traveled. The default settings on Tracker automatically make the right direction on the x-axis positive, which is why the graph has a positive slope. However, this does not really matter. If the axis were to be flipped, the basketball would be moving in the negative direction, but the magnitude of the velocity and total distance traveled would be identical. Next, I created a computational model of the movement of the basketball using computer coding. To create the computational model, the code needed to be changed to model Newton's second law. The most important thing was to change the net force to equal zero, since we were trying to model constant velocity. It is important to realize that having zero net force does not necessarily mean there are no forces acting on the object. There can be pushes and pulls, but they should cancel each other out if net force is truly zero. The next thing I did was set the ball's velocity to Newton's second law. The final velocity had to equal the initial velocity plus the force over mass times time.